welcome back to the technology track. If you don't mind, could I get a quick sound check to make sure you guys can hear me? If you could say, yes, I can hear you in the chat. Okay, great. Thank you so much. This block is going to focus on, let's see, digital workflow and manufacturing 4.0. We have some great speakers that will be speaking about their digital workflows, some mathematics, how data is handled, and just so many other topics. Our next set of speakers are coming from Dyndrite. Sorry, my notes are a little scrambled. Dyndrite and Galt Consulting. We have Lurati.
Hey.
Hi. And we have Jennifer Ferello. Welcome, ladies.
Thank you.
I'll to you to introduce yourselves and your companies, and thank you so much for being here.
Thank you.
Well, I guess I'll go first since I'll be asking some of the questions. My name is Jen Ferello. I have been in the industry, well, in the software engineering industry for most of my career. Just recently started Galt Consulting, which provides business development and marketing services to a wide range of companies. I've worked a little bit with Dyndrite on the side and working with some other vendors as well. But I just want to turn it over to Lauda to introduce herself. Matter of fact, since Amy, I thought you were going to read the introduction, I'll just kind of lead in with Lauda. Why don't you tell us just a little bit about your background, kind of where you can touch on university as well, but kind of what led you to the additive manufacturing industry and into Dyndrite in particular.
Okay, absolutely. So let's see. I'm an applied mathematician by training. So I studied math and computer science in undergrad, and I got my PhD in applied math. So I specialized in numerical PDEs, and basically that's just scientific computing. So a lot of mathematics, but a lot of computer science there as well. And as I was going through that, I wasn't really sure what I was going to do, but I knew I didn't really want to teach, and I wanted to work on real world applications. So what I focused on was breaking into industrial mathematics, which I'd heard about. And so I landed at the Institute for Mathematics and its Applications for my postdoc. And the Institute actually does a really great job of pairing academics with industry. And so they paired me with Boeing. And specifically, they placed me in the Boeing Applied Math Group for my postdoc there. And this was pretty much life-changing experience for me. It really just set my career in a direction that I hadn't really imagined before. So I spent a couple of years there, and then eventually I was actually hired in. So I spent probably in total 8 years in the geometry and optimization group. And while I was there, I was basically working with engineers across the company because it was kind of like being an internal consulting firm. But I was also working with like a large group of mathematicians on my team to basically build software tools that helped engineers across the company more easily design products. So we were focused on optimization and also on geometry for manufacturing. And I would say that the experience of being at Boeing is really where I got to understand the power of mathematics and of abstraction and automation and how important it can really be in a production environment. So I was having a great time. This is a long story. I apologize. And I got impatient though with the pace of things there because I was young and Boeing's a big place.
It could be a little slow.
Glacial pace. And so I was eager to make a change. And so I shifted to an established startup that was still kind of small called Redfin, and I made the pivot to data science for basically the next 4 years, where I got to see what it was like to see a medium-sized company grow to a really big one, see them IPO. I got to work on helping people buy homes, and it was just this entirely different side of math, which was rewarding in a really interesting way. And what I found is that I really liked being at a small company because you just have outsized impact. It's just so much more than you can do as an early career individual at a really large firm. So towards the end of my time there, I was actually contacted by one of the co-founders of Dyndrite, and this person was actually an old colleague of mine at the Boeing Applied Math Group. And so he starts talking to me about how they're launching this new tiny startup and they're focusing on geometry for manufacturing. And what do I think? And, to me, it seemed like a no-brainer to just make that jump because it was just the combination of two things that I found that I loved, the small company and then just going back to the geometry for manufacturing.
So really kind of a very natural fit for you then.
Yeah, it's been wonderful.
Best of both worlds.
Yeah.
Getting into our discussion today, the reason for our session was really to the contention that manufacturing needs a math department. And math is certainly not new to manufacturing. I think it's been used since manufacturing has been done. Certainly, the more it's involved in calculations and calculators and computers, it's used from product design to the manufacturing itself, within budgeting, et cetera. So arguably, it could be said that manufacturing already has a math department. I'm assuming since you want to talk about why we need it, there's got to be something different that Dyndrite is doing, a different approach, a different view that you're taking on it. So can you tell us a little bit more about that then? What's different about Dyndrite's approach?
Yeah, absolutely. Yes, math is absolutely, it's embedded in engineering. It's the language of it, really. So I think what I'd say is that right now, manufacturing has math departments. In fact, it kind of has like competing math departments, and they're all proponents of these different approaches. And the reason I say this is because I feel like the tools out there that exist right now for additive manufacturing, they basically, you can divide them by sort of the geometric representations that they support. So some of them, support splines, pick your particular flavor of splines. Others are going to, require that your geometry be defined by implicit functions. Those are really popular again. Others are only going to handle STLs, OBJs, 3MFs, things like that. So as an end user, your design's geometric representation, it basically dictates what software you can use. Mm-hmm. Or conversely, if you're really focused on using one specific software suite, then you're going to have to fit your geometry representation into what that tool can handle. So I would say it's just a little bit more narrow. So what we're doing a little bit differently is I always say that we have a more geometry agnostic approach to things, where what we're trying to do is develop algorithms that are really useful for multiple different representations so that customers can choose the one that's best suited for their process instead of sort of being funneled into one. And you really want to make it easy for people to convert between these different representations so they're not locked into what they can do because of the geometry. So that basically makes our engine like really flexible, and it allows us to piece our internal tools together in different ways. And it really leaves a lot of room for us to add new ideas and new approaches as the field develops and matures, and just new ideas come to the forefront, because that always happens. And to me, I don't know, I always think of abstraction as a very math-centered approach, because in math, you don't sit down to solve an incredibly specific problem. You really focus on solving a class of problems. So basically, you say, you sort of lay out the constraints or the, what's the right word for it?
Parameters?
Parameters, yeah, or, the features of a problem. And you basically say, if my problem has these features, then these are the approaches that work for it. And so that's what we're doing. And so even though I'm talking to you guys today about 3D printing or additive manufacturing, we're not actually writing an engine that's geared towards additive manufacturing. It's about geometry. And so it's actually can be easily used in many other areas of manufacturing. And I think that that's the flexibility that's really important. It opens up, the user's choice of software. It allows you to put together the tools that are important to you instead of limiting what you can use. We're just always trying to promote that freedom. And I think that that does make us a little bit different.
Oh, I definitely agree with that. I've dealt with enough geometry in my career that abstracting the format really does free you a lot. You're right, tying you neither to a software or to a particular approach. I'm curious, since you're right, abstracted math basically applies. It can apply anywhere within manufacturing. Why did you choose additive to start with? Whereas, why additive? Why are you talking here at this conference and not at a different conference on a different kind of manufacturing?
Yeah, absolutely. So yes, as much as I'm a big proponent of abstraction, you actually have to start doing something and work on something real. And I think we felt that this was a spot that we could really make a big impact. I think what I've found is that when you're working in software engineering, it's really useful to have customer problems guide your development, because otherwise you're just sort of floating around and not really directed. And so having a customer problem really guides you and helps focus you. And so that's really important. And what we kept hearing was that, these large STL files, they're a big pain point for people, that build prep is slow, that, the software that exists is kind of choking, and that people can't print what they want to print because the files are just complex and the tools can't quite handle them. So to us, it sounded like, okay, you've got this trade-off between the precision that you want from your processes and then the data size and the speed that you can get those solutions. And basically, like, if you want to print a machine resolution right now and you've got a really complex CAD file and you have to tessellate that, to get it into your build prep, that's going to be a really huge file. And that's the state of, a lot of the tools right now. And so we asked ourselves, like, what if you didn't have to do that, right? What if you could just keep your CAD data, do build prep on that instead? And basically that helps in two ways. It helps to, reduce the amount of pre-processing that you have to do. So making a mesh, cleaning the mesh, which, is another thing that people don't enjoy. And then you sort of postpone that data processing stuff much closer to the machine by discretizing as you're pushing this information to the machine. And so what you get from that is, the benefit of higher accuracy, but less work in like pre-processing, and you get that speed as well because you're not having to process as much data.
Right.
But the thing I want to come back to, though, is we're not trying to get rid of STLs, right? Because STLs are around, they're used in a lot of places. Like I just got my Night mouth guard 3D printed, and that was, that was a mesh generated from scan data. They're not going away. In fact, I feel like they're going to be coming in from different directions. But I think it's important to have more than one path. And so that's really what we're trying to do, is like provide an alternate path. And so that was sort of the first thing that really guided us into this area.
Right. Well, and I can certainly understand that. So aside from, moving manufacturing closer to the original design or where relevant, and, arguably taking out a number of steps and perhaps even some data corruption, which can happen during a translation process. What are some other areas that math can be applied within the additive manufacturing space?
Okay. So I think that I want to touch on something that's, in my mind, math adjacent, right? Because I feel like the math itself for 3D geometry manipulation, it hasn't changed, but how we deliver that math solution, the numerics, the computation, it needs to change. And the reason for that is, a lot of these tools that we use right now, they were written in the late 70s and 80s, 40 years ago. And
ouch.
Ouch. I know. And they were absolutely, they were state of the art back then. But if you go look at how we thought about algorithms back then, it was all about, flops, floating point operations per second. But we live in a very different world now where, flops are never free, but it's closer to that. And just for context, the first supercomputer that was built, the Cray in 1975, had like 80 million flops. But the graphics chip in your iPhone is close to like 80 gigaflops. So we're talking like a whole lot of power just in your cell phone. And when you start talking about laptops and servers and supercomputers, well, it's obviously, the architecture has changed substantially, and the algorithms that we're using to compute these same math solutions need to change also. So that's really what we're focused on right now. And that's, when we talk about the accelerated computational engine, the A for acceleration is all about reworking some of those algorithms to really leverage things like multi-threading on the CPU. GPUs, of course. GPUs are a really great match for most of these algorithms because GPUs are really performant on simple math operations. And that's what's underpinning everything in CAD and CAM software. It's math.
Right.
So our goal really is to just build an engine that's going to scale with your computing capabilities, right? So we want that same tool to work really well on your laptop, the one that you have at home, but also you want it to scale up and get even better performance when you're on a server or a cluster. So basically, the more computing power that you're throwing our way, the more performance you should be gaining. And that's I think, the new way forward for a lot of the tools.
Right, to be able to really take advantage of that hardware underneath then.
Yeah, absolutely. And then I think the other thing, I'm going to keep talking, sorry.
That's fine.
The other thing I do want to touch on, though, that I think is important, and this really goes back to the time when I was at Boeing. One of the things that I really learned was that repeatability and automation, they're really critical for production. And, not just for production's sake, but for the whole design pipeline, for being able to enable more advanced mathematical approaches. So maybe it's design of experiments for calibration or for testing new materials, or design optimization or simulation. All of these different methodologies that I think as you mature as a manufacturing industry, you want to start incorporating all of these things into your process. They all require the ability to basically reliably generate results in an automated way. And so that other thing that we've been doing is focusing from the very, very beginning on building that automation capability into our engine with a Python API, which we feel is, it's a very friendly language. So it doesn't require, setting up a custom software development shop if you want to use it.
No, it definitely does not.
Yeah. The friendliest one out there, if you ask me.
It's the closest one to the English language. I will give you that.
Yeah, totally.
And it's well tested, certainly, because it's been around for a long time. But I think the use is certainly increasing with the flexibility and the realization that so much of what we do these days can be automated. Certainly, I think that this last year has shown us a growing need to move towards automation wherever possible, so they can have that hands-off, lights-out sort of continual production.
Yeah, absolutely true. Absolutely.
So one element that really came through in some of the things you were talking about is basically the recapture of time, whether it's in the front end where you're removing as much of the pre-processing as possible by moving CAD and manufacturing much closer, or it's the GPU acceleration, or it's the move towards automation. That's what you're doing there is recapturing time. And of course, everybody knows time is money. Certainly in a production environment, obviously the more quickly you can produce, the more either different things you can produce or the more parts you can produce. Aside from reducing time and cost, where do you see as the next big area where math can basically assist in increasing, where's our biggest challenge as in the industry, in the additive manufacturing industry, where math can play a significant role, both in creating the problem and fixing it?
Yeah. So the spoiler is, I think it's data. I really do. I am just amazed at the scale of data that this industry is producing. We're all trying to move towards large scale production, and as you start to see that, okay, we're removing the bottleneck of speed, you can kind of start to peek and notice what the next challenge is. And that's the enormous amount of data that goes into a 3D printing job. It's easily just terabytes and terabytes of data to describe just one build volume job. And the problem is not getting any smaller. The scale of the printers is getting bigger, the precision is getting even more precise, and the processes, the things that we want to incorporate are getting more complex. You hear people wanting to bring machine learning into the mix so that, they've got these adaptive processes. Every single one of these things, adding simulations, adding design optimization, everything just keeps like upping the data requirements. So in my mind, everywhere I turn, I see data management, data flow as the next big problem the industry is going to tackle. And I have noticed actually that academia is also pivoting to the same field. They're starting to think about big data. I mean, there's a lot of stuff already in the area about taking large data and sort of figuring out the sparse representations for it. And so there's a lot of math that you can sort of bring to bear on this. That's, it's been around for quite a long time. We'll see how much of it can help or how much new research really needs to be done. But I really think that that's the next big issue that we're going to face. And that is why I'm especially interested in hearing Janet's talk, which is
I know, I saw that coming up. Yeah, that's due from now.
Eliminating data. Like, all right.
No, I agree.
Let's see. I would love to get rid of this problem.
I saw that as well, so I'll definitely be in that one.
Yeah.
So real quickly, kind of watching our time here. I know we're running short. So one of the things I want to touch on, or I wanted to ask you real quick is, I know from my own experience, one of the most exciting things about working for a small company, a startup, is not just the flexibility that you mentioned and the agility, but also the fact that everybody's working towards the same goal. And the periods of generally speaking, they're a burst of growth. Is that something that you're seeing at Dyndrite too? I mean, the industry itself is definitely growing in different bursts. Are you guys doing the same?
Yeah, we actually are really fortunate not only to not have had to downscale at all during this pandemic. We were all able to keep our jobs. We've all been working from home, which, not everyone can say that. So we're really lucky. But we're also even more lucky that we're growing right now. So we're actually going through a hiring spurt at the moment. And we've got some job openings in product, in marketing, and my team, the engineering team, is planning on opening a couple of positions in a couple of weeks, actually. So there's no shortage of opportunities to join us if
hopefully you
really
can help continue to elevate the industry and its diversity initiatives too. Since I would guess most of the people listening are women. So,
we have a really women-friendly engineering team where our team's composed of like 30% women, which is, pretty good for tech.
That's really good for tech.
Yeah.
All right. Well, I think, Amy, we're a little bit out of, we're a little bit over actually our time here, but
sorry.
No, that's okay. Just a little bit. So I want to turn it back over to Amy to see if there are any questions coming in or where you want to go from here.
Yeah, so I think this was such a good discussion. We don't have any questions yet. But yeah, I think you guys covered it. This is such an important topic. If you don't have any other thoughts you want to share, Laura, then we can just give everyone a little bit more of a break between talks, but it's up to you. Any closing thoughts?
I think I've talked more than I normally do out of yeah. Happy to answer questions if anybody's got them. But, my talking quote is done for the day.
All right, sounds good. So we'll go back to the tables then. I'll leave you guys at the tables, and then we'll flash up our meeting card here a few minutes before the next talk. But thank you so much. Like I said,
thank you.
It's an important topic. I know it's hard to address. It's just kind of a bear of a topic, but I really appreciate coming on and sharing your expertise with us. And Jennifer, thank you so much for moderating.
No problem. Thanks. It was fun to be on here. So
yeah,
sounds like we'll both be in Janet's presentation in a couple presentations from now.
Yeah, I think so.
All right, thanks, ladies.
Thank you. Bye.